Well, first I'd like to thank the organizers for having me give the very last lecture or the talk of this week. The word is keynote, right? So I'll say very briefly and give and illustrate on a few examples why we care about the cross sections when we do modeling and when we do pretty much anything related to exoplanetary atmospheres. Oops. How does this work? Sorry. Yeah, it doesn't. Okay. Well, sorry again. Great, thanks. Yeah. So, pretty much all the microphysics, all the physics that we have to include will be contained in the cross sections. And every time when we have to deal with any kind of system that contains a gas and photons and dynamics and kinetics, we'll have to input all this information in terms of cross sections. And typically, the things that we are concerned about in here are non-thermal processes, escape, energy deposition, relaxation within the hot atmospheres, perhaps different physical regimes, and perhaps some traces of exotic physics that we don't really expect just by making a comparison with the solar system. So, since it's the last talk, I'll put this slide on. So in terms of what I mean usually by cross-section, what everybody means is that we have some sort of flux, particles or photons. There's a scatterer, they scatter, and we observe it in some solid angle. And typically this would give us a number, a surface. However, we can also speak about differential cross-sections, which can give us this distribution of this number with respect to the angle, or double differential cross-sections, which also includes the momentum information. And also, we constructed all kinds of probability density functions from such cross-sections. And finally, the diffusion cross-section, which is used in all transport theories, will be constructed from basically information about the differential cross-section. For example, the diffusion limited escape will be completely determined by this parameter. So there are a few examples that we typically all encounter. For example, the photoionization cross-section for something is going to be 10 to the minus 15 square centimeter. Then we can have usually some sort of exponential or logarithmic behavior, so some sort of function. Let's say the argon and oxygen colliding can be described as a function of temperature using some sort of function like this. Or finally, we just import something. And then we run the simulation. We usually need hundreds or thousands of cross-sections like this to describe the chemistry or whatever we're interested in. And that works fine. For example, I found this subroutine in one of the codes that you used for modeling. It's called fake diffuse cross-section. So it constructs the H2 argon reaction and elastic scattering cross-section based on the oxygen argon, which is not exactly the same thing from a point of view of chemistry. And then there are things like this. Then a few years ago, I did a calculation where I was looking at the oxygen plus H2 reactive cross-section. So purely reaction at pretty high collision energies. So this would be in electron volts, between 10,000 and 50,000 roughly. And then I talked to some astrophysicists who were interested in PDRs or photodissociative regions or photon dissociative regions, who used the previous results, which ended up going, following a power law and increasing very rapidly, resulting in the estimate of prediction power output of one of these PDRs by 11 orders of magnitude, which is not good. So things like this can hardly happen in atmospheric modeling, but they could happen at a smaller scale. 1 or 2 orders of magnitude could happen easily. So just briefly, how we usually obtain these kind of cross sections. We look up the experimental papers if they exist. And it's great if they exist, but very often they will not exist for the temperatures that we care about, or for the states that we care about. So we interpolate them, we approximate them. Or we can calculate them. We can calculate them from the first principles using less or more sophisticated level of theory. A commonly used approach is so-called hard sphere approximation, which is really assuming that there is a hard sphere potential. Or we can do a slightly better job. We can actually calculate the ab initio interaction potentials using the methods of quantum chemistry. So where one or more electrons are considered in such a calculation. So I think yesterday one of the speakers presented magic. This is kind of dark magic. So if this is done correctly, it can lead to pretty good results. This is an example of sulfur colliding with xenon. These are the 3 lowest states going to the lowest asymptote. By the way, this is the Lennard-Jones potential coming from the NIST reference, which should represent the green one, really. It's different. When we add additional terms, things can get much, much nastier. And usually for doing any kind of spectroscopy of extrasolar planets, we will not care about this because we usually have really hard time getting even the really, really basic spectra. But people in the lab do care about this. So in a way, the state of the spectroscopy of extrasolar planets is comparable to what the laboratory atomic physics was about 100 years ago, which is pretty much good news because there's plenty of room for improvement, and then we'll be able to learn many, many things about these objects. So I'll give you one example. It's a case of non-thermal escape from Mars. So this is a diagram from the NASA's MAVEN mission team. They were analyzing all kinds of escape processes that are currently active on Mars with the idea to project back in time and try to say something about the evolution of Martian atmosphere. And there's Jeans escape. There's no hydrodynamic escape because there's not enough energy input. And then there are many other mechanisms. The dominant ones are the photochemical escape, so due to the EUV heating, and then various mechanisms that will strip the ions away from the planet. So I'll specifically give an example for photochemical escape. And for example, the dominant projectile that's being created by photochemistry, by the dissociative recombination of oxygen 2+, are hot oxygen atoms. And they can collide with, among other things, with hydrogen or deuterium. And they can kick them out of the atmosphere because it doesn't take that much energy to eject hydrogen. And these are examples of a detailed quantum mechanical cross sections for such a process. And then there is clearly a difference between red and the black curve for H and for D. And also this would be the OH diffusion cross section, which will govern the diffusion of hydrogen in such a process. Now, the important thing here is that when this is compared to the hard sphere, these cross sections will have pretty strong anisotropy. So this is caused by the fact that the long-range forces are not going to be fully spherically symmetric. And there's also the process is directional. So it's not like scattering in all directions equally. And because of that, there'll be some effects. For example, if I look at differential cross-section for the same process, this can be reflected in different sizes of, or different amplitudes of these little oscillations. And as we go down in energy, this becomes more evident. But then the forward peak increases as we go up in energy. So this becomes important for example, for more energetic processes like a solar wind ions coming in. If one calculates the hard sphere approximation, so hard sphere cross, just a hard sphere cross section versus the fully quantum, the result will be 49% of hydrogen after these kind of collisions will be able to escape. Enough energy gets transferred. This is what the HSA would predict, versus the 19 that could escape according to the fully quantum model. That's different, and that's just one energy. Then it gets worse. We can add molecules. Molecules have internal structure. They can react. So even a simple case like this actually is pretty difficult to analyze in some cases, because this kind of reaction between oxygen and hydrogen, especially at higher temperatures, will go through some short-lived transition states, one or more of them, as they actually pass next to each other and then get scattered in different directions. So if that is accounted for correctly, then such a quantum mechanical calculation can actually reproduce detailed distributions of rotational and vibrational states of the H2 or of OH in such a reaction. And then that can give us lots of information about what's going on if we can measure that. And for example, at higher energies, this would be a good target for far infrared or millimeter wave, or at very high energies, for radio telescopes. So if something like this would take place at one of the candidate planets, maybe there will be a way to extract some information, perhaps in the future. Again, there are differential cross sections, and then note the very strange oscillations that appear for low energies here. And then each of these ripples will reflect something that's going on with respect to the inelastic processes. And finally, when all that is put together, we can get this kind of graph, where, for example, these two curves would correspond to two cases of Jeans escape, which is dominant for hydrogen, and then there would be a photochemical escape of hydrogen with all these processes taken into account, and finally the contribution from the solar wind energetic neutrals. And so one thing that I propose as a project to work on would include H colliding with CO or H2 colliding with CO, where within the next 5 weeks, I guess since I have no students to work with, it's going to be myself. I may actually look at a very approximate level of theory how the way that the CO2 gets excited by these kind of collisions. And then once CO2 gets excited, it will radiate. And that could indicate to what extent will a small fraction of CO or CO2 in such an atmosphere affect cooling in this type of planetary atmospheres. Finally, a bit of advertisement. So actually at NASA Ames, there is a quantum chemistry and molecular spectroscopy theory group that deals with astrophysical and atmospheric processes. And in particular, what they're trying to do, they're trying to refine the high temperature spectra and spectral lines that are used, for example, in HITRAN. Because we know that HITRAN doesn't work very well for many things at high temperatures. So for people who are interested, take a look at this website. And currently, there are CO2, ammonia, and SO2 for certain temperature ranges. And roughly, the people who are working on this, they include between 10 and 30 times more lines in there, which means that some parts of the spectrum that HITRAN would predict may be, let's say, up to 30% inconsistent. And finally, this is my last slide. So, thank you. Depends on how large the system is. So for things like oxygen plus hydrogen, they're better because it's very, very difficult to deal with neutral hydrogen. For things like oxygen plus H2, they're fairly good. We can meet at below what is called the chemical precision. For larger systems, it depends on the system, I think. So depends on the, let me think. Do you have some specific system in mind, or? No. Oh, I mean, when it comes to cross sections, it can be 50% easily. Yeah, it can be much more like the graph that I showed for the PDRs, where people use the experimental points and then just extended them. Yeah, I mean, my feeling is it's difficult both on the side of laboratory astrophysics measurements and on the side of theory.
Question about the Raymond mission.
Yeah.
Are there particular cross sections that should be looked at that potentially fundamentally change our interpretation of the observation?
Well, methane. Yeah. Then maybe ions, because usually, I mean, typically the collisions involving ions are less well known, because ions tend to have longer interaction potential. So I think I never tried doing anything with condensate. Yeah, there are people who do it, and actually in the chemistry community, one of the really hot topics these days are reactions on a surface. So, and of course that's related to synthesis of molecules on dust, for example, which is I think of lot really of interest in astrophysics. I'm not sure how much it's here, but I think it could be.
Marko again?